Hello and welcome to the practice problems video for approximating and computing area. Alright, so given the following chart of f of x versus x, so we're given the x values and what their function values are at each of those points, we're going to compute the r sub 5 and l sub 5 over the interval 0 to 1. So r sub 5 is the right endpoint approximation using 5 sub-intervals, and L is the left endpoint approximation using also 5 sub-intervals. So the first thing I always like to do when doing anything is write down what we need to find. So we want to find r sub n, specifically r sub 5. So what I like to do is write down my sub-intervals. So the first one is 0 to 0.2. Okay, the next one 0.2 to 0.4. The next one 0.4 to 0.6, and then we have two more 0.6 to 0.8, and then the last one 0.8 to 1. I'm going to squish that in. So that last one is a 1. Okay, maybe I won't squish that in so you guys can see it. So the last one is 0.8 up to 1. Okay, so once we have, and I like to check 1, 2, 3, 4, 5 sub-intervals, so we're good. So this 5 is accurate. And then what we're going to do is note that we want to take the right endpoint. So what I do once I have my sub-intervals is I circle the point that I want from each of them. So I'm going to circle the right number. Okay, so this is the right endpoint, so we're circling the right number of each sub-interval. Okay, so these are our important values here. So 0.2, 0.4, 0.6, 0.8, and a 1. All right, so these are our endpoints, our right endpoints. So that means we're going to take r sub 5 is going to be equal to delta x, whatever that is, the length of our sub-interval, right? And then we're going to evaluate the function at each of our right endpoints. That would be f of 0.2, f of 0.4, f of 0.6, and then f of 0.8, and lastly f of 1. Okay? And to solve for delta x, all you have to see is how long is your sub-intervals. So that would be 0.2, right? 0.2 is the length, because that's what you can get by subtracting the endpoint of your subinterval from the start of your subinterval. Okay, so now that we have that, we can just plug in the values that we see, because we're given these f of x's, right? So we get r sub 5 is equal to 0.2 times, and f of 0.2 is here, that's 48, so 48, plus f of 0.4 is a 46, 46, and then we have 44, 42, and a 40. Alright, so ultimately we're just going to get that r sub 5, once you plug this into your calculator or do it by hand, we're going to get that this is equal to a 44. Alright, so let's do the left endpoint approximation on the next slide. Alright, so here's our chart again, and what we want to find is L sub 5. So again, I'm going to create those little sub-intervals, right? So 0.2, that's a point, 2 to 0.4, and then 0.4 to 0.6, 0.6 to 0.8, and then 0.8 up to 1. Okay, so now that we're doing a left endpoint approximation, I'm going to circle the left value. Left, 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 and left one. Okay, so our important values are the ones that I circled, and then we're going to have L sub 5 is going to be equal to delta x times f of 0 plus f of 0.2 plus f of 0.4 plus f of 0.6, and lastly f of 0.8. Okay, and again, our delta x, our subintervals didn't change, so they're still going to be of length 0.2. And then for f of 0, we get a 50, that's what we're given in the table, and then we continue on, so then we have a 48, and then we have a 46, and a 44, and finally a 42. Okay, so again, when we calculate this, we're going to get that L sub 5 is equal to 46. So this approximation, even though we had the same subintervals, the same values of our function, this because we measured it using the left endpoints as opposed to the right, this one was a little bit higher. Okay, and just as a reminder, our R sub 5 was equal to a 44.